Hello.
Thank you very much.
All good.
Wonderful. Okay. Welcome everyone. Hello. Yes. So I think most of you have heard the bad news at this point. It is unfortunately cloudy. Again, I feel like I'm saying that a lot at the moment. So instead, we are having our cloudy evening routine of talk from one of our researchers here, followed by tea and biscuits, followed by a couple of talks from the CAA. One about the history of Cambridge astronomy, and also a planetarium show showing you what is behind the clouds. So one thing I do want to mention, just some housekeeping before I introduce our headline speaker. In about 3 weeks' time, 2.5 weeks' time, we have our big open day here. So that's going to be on Saturday the 16th of March, starting from 2 p.m, just where you came in today. We are open as part of the Cambridge Festival, and there's going to be an entire afternoon of astronomical games and talks and activities. No need to book, all completely free, so just turn up here from 2 p.m. There's all kinds of things. Some students are designing an interactive go inside a black hole room. There's going to be arty activities. There's going to be some homemade 3D printed telescopes set up. All kinds of amazing things. Yeah, Saturday the 16th of March is the date for your diary, and hope to see you there. So, I'm just going to introduce our headline speaker. So we've got Dr. Matt Grayling, who's a postdoc here at the IOA, who studies cosmic lighthouses and uses them to understand the universe. So he's going to tell us more. Matt.
Thanks very much for the introduction. Yeah, thanks very much for that nice introduction. So yeah, my name's Matt. So yeah, I'm a researcher here, and today I'm going to be talking about type 1a supernovae and how we can use them as cosmic lighthouses to chart the history of the universe. So just to give you an overview of what I'm going to be covering in this talk, there's going to be a bit on what supernovae are. I'm going to talk about how we can use them to map out the universe, and then I'm also going to talk a bit about the future of supernova science. So first question is, what are supernovae? Well, they're big explosions, so they're exciting in that sense. We'll probably will take questions at the end, but there'll be plenty of time for questions later. So supernovae, so they're massive explosions that occur at the end of lives of some stars. And they are incredibly bright, like super, super bright, incredibly energetic. The way I like to put it into context is that typically a galaxy contains something like 100 billion stars, huge number, but the explosion of just a single one of those stars in a supernova can be brighter than all of the collective light of all those 100 billion stars put together. So yeah, they're very, very bright. They're also of great interest within astronomy. So they have, they have lots of exciting unknown physics relating to the actual explosion themselves, what's going on, how they're producing so much energy, and also the impact they can have on their surroundings by expelling out, throwing loads of material out, producing loads of energy. So the picture you can see here on the right, this is a picture of the Crab Nebula. So this is actually a supernova remnant. This is the material that was left behind by a star that exploded in 1054. So you can see they can spread out and expand into their surroundings a lot. And as I mentioned, they can also be used to map out the history of the universe. So to put into context what supernovae are, we need to think a little bit about the life cycle of a star. So what a star is fundamentally is just a big ball of gas that is burning, undergoing nuclear fusion in its core. If you think about a star like the sun, spends most of its life burning hydrogen into helium, then spends a little bit burning helium into heavier elements, and then when it runs out of fuel, it stops. So this follows this kind of top path you see here. When the star runs out of fuel, it kind of sheds its outer layers, and you just end up with a remnant left over that's called a white dwarf. So basically just hot remnant of the star that just kind of sits there not really doing a lot. The other alternative you can have, if you have a really big star, it can keep fusing heavier and heavier things, heavier than helium, until it eventually runs out of fuel. And because it's so massive, when it runs out, the core collapses. It collapses smaller than a white dwarf because there's so much material. Eventually, it reaches a really compact core that just can't be compressed anymore. So all of the material that's surrounding it rebounds off that, and you get a huge explosion shooting out again. That's what's known as a core collapse supernova. You can see, so if we look at the types of supernovae, you can see there where the core collapse supernovae come from. They encompass a huge variety of objects. We also have a specific type, which will be the focus of this talk, which is a type 1a supernova. So these originate from white dwarf stars. I mentioned previously, white dwarfs just kind of sit there not doing very much. That's true if they're by themselves. But if you have a white dwarf with a companion, interesting things can happen. So if you can see in this picture here, the little white dwarf is the white dwarf. If it's near, say, a massive star, what can happen is that it can interact with that. It can gain material from that massive star. That companion also could be another white dwarf. The thing is that about white dwarfs is that they are stable only below a certain mass, about 1.4 times the mass of the sun. So if you have a setup like this, where you have a white dwarf that's gradually gaining material, eventually it hits that limit where it becomes unstable, and then it starts to ignite and then explodes as a supernova. So that's another way to get them. The thing that's interesting about type 1a supernovae is because they're all linked to this kind of mass where they become unstable, they all explode around that mass. They're all very similar. So if we look at the core collapse supernovae, they're super interesting, but they have very, very diverse properties. If you look at the type 1a supernovae, they're all pretty consistent because they're all exploding in this same scenario. And that's going to become really useful later on. So you can see here is just a quick illustration of kind of roughly what's happening. So you have white dwarf gaining material, eventually becomes unstable, and you have this huge explosion that occurs. So that gives you a bit of context about what supernovae themselves actually are. I'm next going to talk about how we can use them. So this is a figure that some of you may have seen before. This is the entire history of the universe just expressed as a very nice graphic, essentially. So on the left, we have the Big Bang. So we start with the initial singularity. We have an expansion out. The universe expands, continues expanding up until the present day. As that happens, the universe cools over time. You end up producing stars and galaxies. Keep evolving that through, and we get to where we are today. Now, there's a lot of information that we can learn about the universe from that expansion. So to give you some examples about what might happen, the universe could just keep accelerating out forever, or keep expanding, getting faster and faster, bigger and bigger, going out forever. You might have the exact opposite. Maybe the universe will keep expanding out to some limit, and then it's going to collapse back down again. You might have something roughly in the middle where it keeps expanding out, but progressively slows down, ends up at a roughly constant size. The way that the universe evolves, if we can track how it's grown over time, we can learn both about what it's going to do in the future and also make conclusions about its fundamental nature and what exactly makes up the universe. We can do that using type 1a supernovae. I'm going to give you an overview of how we can do that. So there's two main things we need to worry about if we want to map out the universe in this way. So the first one is age. We want to look at how old something is. We can do that in a slightly roundabout way. So this, I promise this will become relevant. So the Doppler effect is crucial to this. For anyone who's unfamiliar with it, it's an effect that everyone in this room will have experienced. It's the effect that causes ambulances to sound higher in pitch when they're driving towards you compared to when they're driving away from you. And the reason that happens is that if you have anything that is a source of waves, whether it's light waves or sound waves, that's moving relative to you, you can end up with this effect you can see in the picture where those waves either all get bunched up or all get spread out. So that changes the frequency and the wavelength that you observe. We can think about how that applies to astronomical sources. So because of the Doppler effect, if we look at something that's moving away from us, then the wavelength gets longer, which means that it appears redder to us than it actually is. And the opposite is true if it's moving towards us. If it's moving towards us, then it would be blue shifted, appear bluer than it actually is. So we can use this effect to work out how fast things are traveling relative to us. So we can do that by looking at the light from these sources. So there's a kind of a rough illustration of this on the right, but just to summarize, different elements, the different things that we see have different kind of characteristic colors. So you may have experienced this in a chemistry class. If you've ever seen someone putting a bunch of different elements into a Bunsen burner, they all glow different colors. We can identify things based on the light that they emit. So if we look at something on Earth, we can see what it looks like. We can look at an astronomical source, and we can compare what the light the astronomical source looks like to what we know it should look like if it was motionless. And that allows us to work out how fast it is moving relative to us. And this is a quantity that we call redshift. It's just a measure of how much the light has been redshifted. And I will come back to this, but the redshift, it turns out, is very closely related to age. So the good thing, this is something we can measure. We can look at a type 1a supernova, we can get a redshift for it. But that's only half of the story. The other thing we need to know if we're going to be able to map out this expansion is the distance to an object. As it happens, type 1a supernovae are also really good for measuring distances. So if you look at something in the sky, working out how far away it is actually quite a difficult problem. There's a few different methods you can use, but in general, it certainly takes a bit of work to do. The reason we can do that is for the reasons that I mentioned earlier in the talk, which is that type 1a supernovae are all about the same brightness because they're all exploding at around this kind of same mass limit where they become unstable. So we can use them as what is referred to as a standard candle. You can see this illustrated in the image here. But the principle is that if you have something, and you know how bright it is, if you move it a bit further away, as you can see the candle here, same candle just further away, it appears a bit fainter just because it's further away. As you keep moving it further and further away, it will get progressively dimmer. But if you know how bright it is, and you look at it and see how bright it appears to be from the distance you're at, you can use both of those measurements to work out how far away it must therefore be. So in this approach, we can look at type 1a supernovae and use their similar nature to each other in order to work out distances. I should say they're not perfect standard candles, so they're not all exactly the same. So they are what we would refer to as a standardizable candle. So we can apply a few corrections, and that lets us get fairly precise distance estimates using these supernovae. And that gives us the second part of this relation. So the two independent measurements we can get from type 1a supernovae, we can get their distance and we can get their age / their redshift. And we need both of those in order to trace out what the history of the universe looks like. So this plot here just shows some kind of made-up examples of different models of what this might look like. The key thing here is these are models. We can propose different ideas on what the universe might look like, what it might be made up of, and we can make a prediction from that of how distance should vary with age for that kind of made-up model universe. So if you look at the yellow line here, what you can see is that as things are getting younger, the rate of change of distance is increasing. So what that tells us is this would be a universe where the acceleration, or where the expansion is accelerating. It's getting faster and faster as time goes on. If you look at the green line, you see the opposite. This would be a universe where the expansion is decelerating, it's getting slower as time goes on. Or there's also the pink line in the middle where you just have a linear relation. So we can sit there and we can make ideas about what this might look like, but the thing we need is data to be able to test this. So by measuring distances and ages from supernovae, or redshifts from supernovae, we can see where they lie in this space, and we can see which of our ideas the data that we observe in the real universe actually supports. And then that lets us try and learn about the fundamental properties of the universe. So this is a very early example of this type of thing. So this was a plot made by Edwin Hubble in 1929. This type of plot is now generally referred to as a Hubble diagram. And it looks a bit different to what we've seen before. You can see the axes are the other way around. So he has distance on the bottom and a velocity / redshift up the side. But it's the kind of same kind of principle. And this plot was very interesting for a number of reasons. So the first thing is that you can see, if we look at the velocities, they're all positive, they all lie above zero, bar a few, but in general the trend is that everything seems to be moving away from us, which is what positive means there. So that was really interesting just in of itself, because what a lot of people were expecting when you did this type of analysis is that there would be some things that would be moving towards you, there'd be some things that are moving away from you, there would be no overall motion. What this showed is that, well, actually, everything is moving away from us, and implicitly, the universe must therefore be expanding. Everything is getting bigger. So this was kind of the first piece of observational evidence that confirmed this. Now, going from there, what we also see is, or I should say, so once the expanding universe was observed, that also provided a key argument in favor of the Big Bang, hypothesized later, but it's linked together, because if you think about a universe that's getting progressively bigger over time, and you think, well, if you just reverse that trend, go back to where it must started from, everything must have then originated from just an initial singularity, which everything came from. So there's two aspects to this. So the first is just the expansion itself, and we also see this kind of trend that things which are further away are also receding faster. I mentioned earlier that redshift and or the redshift we measure and the velocity is related to age, and this is a nice way to illustrate that. So we know that things which are, we know that the speed of light is not infinite. Light moves very fast, but it still takes time to travel. So if we look at something that is further away, that means that it's taken the light longer to travel to us. So we're seeing it further into the past compared to something that is closer. And by what we also see here is that things that are further away are also moving away from us faster. So what that means is that things with the higher velocity or the higher redshift are also older. That's how the link between redshift and age comes up. So you can think about it in those terms, why we can use that redshift measurement as a proxy for age in that way. So that was how things were in 1929. And so none of those distances on the previous plot were measured using supernovae. They were all using a variety of different techniques, which are only suitable for things that are fairly close by. They don't work generally out to further distances. We need things that are bright like supernovae that we can observe far away because they're so bright in order to get distances for things that are further away. So this plot on the right, at the top, you can see similar thing to what we've been seeing before. Going along the side, we have distance. Along the bottom, we have redshift, or proxy for age. So we can use type 1a supernovae to get these distances. We now have distance estimates for things much further away and much more precise measurements. And what you can see on this plot, not so much in the top panel, as they're all a bit close together, but if you look at the bottom panel, which just shows kind of differences from those lines, you see there's like a solid line, there's a dotted line and a dashed line. And what those all represent are different models of the universe. This is what, if the universe had this particular set of properties for each of them, this is what that line would look like. So by doing this type of analysis, we can use our real data and we can see which one of these lines agrees best with the actual universe, and therefore what are the properties of the actual universe in that way. Now, this type of approach lets us calculate some of the most fundamental properties of the universe. And so that's how things were about 25 years ago now. This type of analysis was done of about order kind of 50 supernovae. But it led to a huge discovery, this data set. So that previous plot compiled two separate analyses that were done, which led to the discovery of dark energy, which I'll go on to explain in so much as we can, but this was work that led to the Nobel Prize being awarded in 2011. So the results of both these analyses found that actually the distant galaxies, supernovae and distant galaxies, were much further away than we were expecting them to be. And what this showed us is that actually the expansion of the universe is accelerating. It's getting faster and faster, which is really exciting and counterintuitive for the main reason that we have absolutely no idea what could cause that. If you think about what we understand about gravity, things attract each other, we're attracted to the Earth beneath us. As things move apart, if they were being attracted by gravity, you would expect them to gradually slow down because they've got a force this way and then come back again. But when we look at the real universe, we're seeing the exact opposite. That expansion is getting faster and faster, and we have absolutely no idea what could cause that. So we denote the phenomenon that is responsible dark energy, but it's really just, we don't know what it is. It's just a cool name that we made up to give it something, but we have no known physical mechanism that's responsible for this. This plot on the right is very technical. I'm not going to go into loads of detail, but what you can do in this type of thing, what they're trying to do is using the supernovae. Along the bottom is basically just the fraction of mass in the universe, kind of mass around us, and then along the side is the fraction of dark energy in the universe. By looking at the distances, they can see what overall picture of the universe seems to be consistent with. And when they do this, we find that dark energy makes up about 70% of the energy within the universe, which is really remarkable when you think about it. That's 70% of everything, the majority of the universe, that we have absolutely no idea what it is. So, I mean, it's unknown to this day, and it really is just one of the biggest mysteries in science. And type 1a supernovae played a key role in the discovery. So, as I say, that was where things were 25 years ago. Where are we now? Well, so that was, as I mentioned, that was with kind of 50-ish supernovae. This plot here shows a recently published paper from the Dark Energy Survey collaboration, which is focusing specifically on this type of analysis, with coming up to 2,000 supernovae. So things have progressed a long way. We can get much better constraints on the properties of dark energy, but there are still lots of unknowns about exactly what it is, and work continues to try and pin down its properties a little better to try and point more to the underlying physics. So I'll just finish up by going briefly over the future of supernova science, where things are. So one thing I've not mentioned so far is how we actually find supernovae. So think about if you're looking at galaxies evolve very slowly. If you look at a galaxy and then you go and look at it again a year later, still look exactly the same. Supernovae are transient in nature. Stars explode, and then they produce loads of light, and then they fade. So supernovae typically last something like kind of weeks to months. What that means is that if you've got to be looking in the right place at the right time to discover them. If you don't detect them first time round, they're gone, that you won't be able to see them again. So early supernova discoveries happened by chance. It was really just pure luck that someone happened to be monitoring the right patch of sky at the right time. As things developed and we started getting more interested in them, we started having kind of dedicated surveys that you would have a telescope that would just look at a particular galaxy, normally kind of a close by big galaxy, every few nights and so on. And every time you just see, oh, is anything different to what it used to look like? Maybe that's a supernova, something new has popped up. And from that monitoring of just specific galaxies, things have now evolved to what we call a rolling search. So that means that a telescope just monitors a big area of the sky, every few nights, keeping an eye out for monitoring new things that comes up, trying to identify new transient sources. And as things have progressed, we've gone from discovering kind of a handful of supernovae every year onto kind of tens, hundreds, and now we're in the regime of kind of thousands of supernovae every year. But that's going to change. So what everyone is very excited about at the moment is the Vera C. Rubin Observatory. This is a new telescope that has been built in Chile. In that building, you can see on the right is, well, I'm not sure it's actually there yet, but it will be there, is the largest digital camera ever constructed. It's going to be incredibly sensitive. And this is going to start a new astronomical survey next year called the Legacy Survey of Space and Time at Vera Rubin Observatory, or LSST for short. So LSST is going to image the entire southern sky every 3 nights. As I say, it's a very sensitive camera. It's going to give us, go very, very deep, get us lots and lots of new sources. So LSST is expected to discover millions of supernovae over its 10-year mission. So a huge step change from what we've got at the moment. We're going to have amazing, fantastic new data sets to try and do this type of analysis with. It's a very exciting time for this type of science. And I should leave you by saying that there's still lots we don't know. So we've got a fantastic new data set from LSST. And the study of type 1a supernovae has come on a long way, but there's still lots of unknowns. I meant if we return to this initial picture we started with of the white dwarf with the massive star. Now, we think this happens sometimes, but there could be a white dwarf and a white dwarf that interact with each other. There could be kind of lots of different things going on. We don't know exactly what systems they come from. We don't know a lot about their explosion physics, about what is actually going on in the explosion that's powering it and making it look like this. And there's kind of few unknown trends that we see in the data. Like I've mentioned before, that they're all about the same, but we do see some trends, for example, between the properties of the galaxy they exist in and the supernovae themselves, which must be telling us something, but we don't know exactly what that is yet. So lots of research is going to try and crack that. And of course, dark energy remains a mystery as well. So there'll be further work to try and constrain the actual properties of it. And LSST is going to provide us a fantastic data set with which to approach these challenges. So yeah, that's the end of the talk. Thank you very much for listening.
Do we have any questions? Yes, right at the back.
So is the world like every single day stretching and stretching, or is it staying the same size? Like for example, you like brought some that you could stretch, and then you started stretching it. Is it like the world is like you brought something that you can stretch it and it stretches?
So it's not quite like that, but it's kind of, so you can imagine the stuff in the universe, the spaces between them are getting bigger, but the actual things themselves are staying the same size. So the Earth isn't getting any bigger, the world's not getting any bigger. But if we look at the Milky Way galaxy, which is the galaxy that the Earth exists in, and look at the distance between that and another galaxy, that distance is getting bigger. So the spaces are getting bigger, but not the things themselves.
Anyone else? Also, right at the back.
You mentioned that to calculate the distance, you extrapolated that based on the expected brightness, and then based on how dim it was, that would tell you how far away. How do you know how bright it's meant to be in the first place?
Well, that is a good question, and it's not trivial, but so basically we have something called the distance ladder. So what that means is there are various different ways you can measure distance, which each only work over certain regimes. So the simplest one is called parallax. So that is just, if you have a star in the sky, when the Earth is on one side of its orbit to the sun relative to the other, the star moves a little bit in the sky, and you can use that to work out a distance. You can use something called a Cepheid star, which is basically a star that's variable, and it has there's a relationship between the time over which it varies and how bright it is. But you've got to go up each step. So to know how bright the Cepheids are, you've got to find a Cepheid star where you can also get a parallax distance. That will let you calibrate the next step up so you can get how bright the Cepheids are. Then for the next step, you've got to then find a galaxy which has a supernova and a Cepheid star in it. And then that lets you calibrate how bright the supernovae are. Now, there are certainly unknowns in the calibration process, so it's by no means a solved problem, but that's the approach to do it. People are trying to think up new, better types of calibrators to do this type of analysis, but that's the general principle.
Thank you.
Anyone else? Please, yeah.
How do you correct for the unknown amount of dust between the supernova and the telescope?
Well, I would say in lots of historical analyses, they haven't, or they've kind of tried to work around it by looking at its color, but kind of not really disentangling the intrinsic color of the object from the dust. The work that, actually a lot of the work that I do is on trying to disentangle those dust properties. So we do that by incorporating explicit dust laws within our modeling. So we can try and do analyses of the overall population to understand what the dust population generally looks like and then incorporate that within our analysis.
You had a question as well?
Yeah. Could you use the light absorbed into it or spiral around it, or if it was far enough away from it, still close enough to be affected by it, and the gravity could bend the wave of light. So could you use that to find different black holes that haven't been discovered?
So in principle, yeah, the idea makes sense in terms of the effect they'll have. The difficulty is that lots of these things are very far away, so often even close by supernovae, they'll just be basically a dot. And as you get further away, the galaxies are often really small, and then it's trying to, the supernovae, basically, if you could get one with enough extended detail to look at what the light was doing as it traveled around, then you could do that. Trouble is, it would have to be close by enough for us to get some detail of the light, and that's just, we have to be very close for that to happen.
Yeah.
Is there any bonds, or is there not bonds, explosions in space that are bigger than supernova, or is supernova the biggest?
Well, there are a few types of different explosions. So there's one thing, for example, what we call a superluminous supernova, which is a particular type that is really, really bright, significantly brighter than the type 1As that I've mentioned here. So those are about the brightest, although we do occasionally find particular example, like there are other types of explosion. We've recently found one that was called like the biggest cosmic explosion ever. I can't remember exactly what type of object it was. It was fairly unique, but you do get them, yeah.
Okay, and should we go for the last question here, please?
Can a supernova be cancelled?
Not without tremendous difficulty. Yeah, you'd have to get it. You have to interfere with the star somehow, and that is beyond our means for the moment.
Amazing. So we have tea and biscuits waiting, and then afterwards we're going to hear a bit about the history of Cambridge astronomy and a quick What's Behind the Clouds planetarium show. Before that, can we thank our speaker again?